Welcome to Hot Chips 25. Session 8, Processors 2.
This is the Processor 2 session. I'm Forrest Baskett from NEA, and I'm your moderator. The first talk is hardware-level thread migration in a 110-core shared memory multiprocessor. The presenter will be Mieszko Lis, PhD candidate in electrical engineering, computer science at MIT. At MIT, his current focus is leveraging fine-grained migration and large-scale multi-core designs. Before MIT, he spent several years in industry where he co-developed the high-level hardware design language Bluerisc. Mieszko?
Hi, I'm Mieszko, and this talk is going to be a little bit different. I'm going to be talking about an academic chip, so it's not the kind of thing you can buy for Christmas next year. But on the other hand, on the plus side, we can tell you exactly what's in it and what our secrets are. So, well, what is this beast? So it's a multiprocessor. It has 110 cores, as many as we were able to fit, given the area, basically. And it's basically like any sort of general purpose processor you might have. So it has unified shared memory that's accessible from every core. It's not a special purpose accelerator like a GPU, so you can run pretty much any program you want on it. The raison d'etre for this chip is it implements fast and autonomous thread migration. So, well, what do I mean by this? So by fast, I mean that migration is entirely in hardware. That is to say, you can count the number of cycles that it takes to migrate a thread from one core to another on the fingers of your hand. By fine-grained, I mean that the decision whether the thread should migrate to a different core or stay on the same core, it's made at instruction granularity. That is to say, at any given instruction, you can very quickly decide that you should go to a different core and execute that very, very quickly. So it's very, very responsive in that sense. And by autonomous, I mean that you basically don't have to worry about it. The hardware will decide for you whether the thread should be in, in core 7 or core 17 or whatever. Of course, you can worry about it, but if you don't want to, you don't have to. And we leverage this migration, this fast migration, to reduce on-chip traffic very significantly. And of course, if there's less interconnect traffic, there's less dynamic power on the chip. So that's the sort of executive summary. In the rest of the talk, I will try to sort of define the problem that we're trying to solve with this chip. I will talk about the chip itself, which we call the execution migration machine, or perhaps somewhat presumptuous, the EM squared. I will talk a little bit about what it costs and what you get out of it. That is to say, what the cost-benefit ratio is. So what are we trying to solve? What is the problem? Well, with these multi-core designs that have lots of cores on them, the on-chip interconnect already dissipates significant power, right? So for example, in the early 2000 MIT raw chip, which had 16 sort of simple RISC cores, already about 40% of the tile power was dissipated by the interconnect, by the on-chip network. And the Intel teraflops, which is some sort of much bigger floating point cores, about 30% of the power goes to the on-chip network. So, and this is of course getting worse and worse. We can make the transistors smaller, of course, up to a point, as was pointed out yesterday. But with wires, it's harder because if you make the wires thinner, you can't really have thin and long wires. You have problems like RCDLA, power, crosstalk, and whatnot. And this is of course getting worse because, well, we can put lots of cores on a single die. But if we have lots of cores, then they need to be fed a lot of data. And of course, this means even more traffic on the interconnect. So where is this traffic coming from? Well, in a typical CPU, you have some private cache, which is generally L1, maybe L2, but let's just say L1 for argument's sake. Then you have some shared level of cache. Let's just call it L2 for argument's sake. And the shared cache is sort of divided among the different tiles in the processor. And when a thread is running, the thread is generally pinned to one core, and it sort of fetches the data from the different caches. But if the workload that you're running on this thread, it exceeds the capacity of the local caches, of course it has to do a lot of communication with the remote slices of the next level cache, and this causes a lot of traffic on the interconnect. And this is not an uncommon problem. Some of the workloads that we've looked at, sort of databases and machine learning workloads, certainly we've seen that this is a significant problem. So what do we do? Well, so locality is good. So if we have these many remote requests, these I don't know, orange kind of arrows, this is bad because, of course, they have to travel quite far to fetch the data. And maybe in a four-core chip, this is not a big problem. But if you have, I don't know, 400 cores, this becomes a significant issue. And we'd rather talk to the local L2 if we can, right? So the solution that we are proposing is, well, instead of fetching the data back and forth, well, why don't you just move the computation, right? So this has the advantage of making the remote accesses local. They're very efficient. And if you have every so often you don't have enough locality, you have to access a piece of data somewhere, you can sort of just have a round-trip message and be done with it. It's kind of like you have cows grazing in a pasture, and they sort of eat the grass in one place. They sort of move over, and they don't really order delivery to where they have already eaten all the grass. So the problem is this requires different hardware than we have today. This requires very efficient migration, which we believe can only be done in hardware. Because if your migration is slow, then even if you have a lot of locality, that would turn these long accesses into these local accesses, then it's not enough to amortize the cost of moving the threads over. So some of our goals in building this chip, if we want to do this migration frequently, then it needs to be fast. So that means that it must not involve any software. In particular, if you're doing migration or thread balancing for load balancing or whatnot, then it goes to the operating system and it takes forever. This is not good enough for us. It should not involve round trips. So you can imagine implementing migration on top of sort of existing cache coherence protocols. But this is also kind of slow, right? Because it's several sort of ping-pong round trips. And maybe by the time you've executed this migration, the ship has already sailed. We also need the migration to be fine-grained. That is to say that because data accesses sort of change as the program runs, this functionality, it has to be responsive. It has to respond very quickly to any change in the data access pattern. Otherwise, we won't be able to take advantage of these short stretches of locality. And for the same reason, it shouldn't really involve centralized scheduling, because you can imagine you have a 1,000-core chip, you have a central scheduler, it gathers data from all these cores, decides what to do, and by the time it sort of sends instructions out, then everything's, all the performance you could have gained is all gone. So if we want to reduce, in particular, the dynamic power, and for this, the on-chip interconnect traffic, we also have to keep the migration small. So there are two ways of doing this, both of which we're leveraging in this chip. One of them is to make the context small, and the other is to migrate only a useful subset. And finally, we wanted a large core count to make the evaluation realistic. And so this is a picture of the layout of our chip. It's 10 by 10 millimeters and 45 nanometer silicon on insulator. It's a little bit less than 400 million transistors. It has 110 cores, as I mentioned previously. They're all homogeneous, so they're all the same. And it has only a single level of cache. And the interconnect is a two-dimensional mesh. So the one thing that this chip is optimized for is efficient migration, and I will talk a little bit about that in a few slides. So each tile is actually pretty simple, and over half of the tile is taken up by the cache. You can kind of see over here that these red things that are covered up by these wires, all of this is cache SRAM. And the rest is taken up by the actual compute core and by some on-chip network routers. One thing that is interesting about this chip is that we have a very custom architecture that makes it a little bit easier for us to do these partial migrations, and it's stack-based, sort of a blast to the past. So we can actually migrate a thread from one core to its neighboring core in as few as 4 cycles. And we can migrate a thread across the whole chip in, I think it's 33 cycles minimum. So, so this is pretty fast. This is, how does this work? In the first cycle, you basically have to unload the thread context from the processor that is running the thread. Then you have to travel however long it takes to the next core. Of course, if it's a neighboring core, it's just 1 cycle. Then you have to start loading the context. And the context has to have the program counter at least, and some of the sort of data that it's going to operate on. So this takes an extra cycle to fetch the other body flit while the next instruction is being fetched. So a minimum sort of end-to-end migration delay is 4 cycles. And the shared memory model that we have in this chip, it's very simple. Basically, we use this large shared cache, and we just use the top bits of the address to decide where a given piece of data can be cached. And so the advantage of this for us is that memory consistency is trivial. The disadvantage is that in the baseline sort of architecture that we have, the loads and stores, which can be atomic as well, they have to sort of be done as round-trip messages. So I send a message to the remote cache. It does the work for me, and I get some sort of results for a load or an acknowledgement maybe for a store. And so this is bad because you might have to repeat this multiple times, because for memory consistency reasons, you cannot cache this data locally in this kind of an architecture, because there's no cache coherence protocol. So we use migration to accelerate exactly this. So instead of making multiple round trips to a remote core, we migrate the entire computation once. We run the thread on the remote core for a while, and then maybe we move to the next location where the data is. So in this architecture, there are 3 ways basically you can access data. One of them is if is this path. If your address is cacheable in the core that you're running in, that is to say, if it's local, then it's easy. You just access your local cache and you're done. The other 2, well, you have to make a decision. If the access is remote, you can either send a remote access request and wait for it to come back, or you can make a migration. And this decision, I will talk about this decision in the next few slides. It's one of the interesting parts of the chip. So how can we migrate? Well, we have a simple sort of migrate instruction that you can just put in your program, and it will just go to whichever core you want it to go to. Well, that's kind of boring. The next more interesting way is when the hardware sees a memory instruction, that is to say a load or a store, it can treat this instruction as a static instruction. That is to say, it will, if the address is local, then it will of course access the local cache, but if it's remote, it will look to the instruction itself to decide whether it should migrate or make a round-trip remote access. Finally, the most interesting part is we have an automatic predictor that sort of learns the data access patterns and can decide for each address whether it should result in a remote sort of one-off round trip or a thread migration. And so this is suitable for for your general purpose programming, or if you're kind of lazy like me, I wouldn't really want to deal with telling the machine exactly what to do. So how does this migration predictor work? Well, it works a little bit like a branch predictor. So it detects long runs of accesses that access this data in the same core. So for example, in here, we would like, if you are, for the sake of argument, running on core A, and you have one access to core B, well, then it's not really worth it to, to migrate the thread and resume execution. So you want this to be a remote cache access. On the other hand, if you have a lot of accesses to the same core, like to the core C over here, then you want to migrate and amortize the cost of migration by making multiple local accesses. And maybe if you have more, then you migrate back to wherever you need to keep running. So the way this works is when the hardware detects that there have been many accesses to the same core, basically as a counter in the core, it inserts the address of this first instruction over here into a lookup table. And the next time around, the next time you come to this, you sort of run and come to this instruction, then it will already know that it should migrate on this address. Another thing that this predictor does is it decides how much of this thread context to take on the migration. You may recall that I said we have sort of partial context transfers. And the way this works is, you sort of start migrating a default amount. And if you migrate and you have to come back because you don't have you didn't carry enough data with you, then next time around, you will migrate with more data. And conversely, if you have to migrate back because you brought too much data and you overflowed the local stack, then next time you will just take less. And finally, because data access patterns change over time, the predictor can change its mind. That is to say, if you migrate to a remote core and you don't make enough accesses to make this migration worth it, then when you come back, this address will be removed from the table, and next time you will not migrate. So in terms of architecture and area, how much does it cost? Well, it costs the costs are similar to a cache coherent solution, right? So our baseline here let's see. So our baseline over here is based on pure remote access, and that is round-trip access for every single word that you have to access. What we add over this, we add this extra core context and some extra routers. This is basically to make deadlock resolution very easy and straightforward, and this migration predictor, which is pretty tiny. So the total area contributions are about 20% bigger in this case, and they're comparable to a solution that implements a cache coherence protocol. And the leakage power is similar. So the question is, well, is it worth it? And the answer to this is, what is the dynamic power? The dynamic power is proportional to the amount of traffic we have on the interconnect, basically, and it's dominated, of course, by, well, it depends on what benchmark you're running. And the advantage is that because both our baseline and our migration-based design access the same addresses, we can just compare the traffic and conclude that that dynamic power is comparable. So, well, how do we do? So in terms of completion time, that is to say how fast our code runs, we do a little better, maybe 20–30% on some benchmarks, which is nothing to sneeze at. Of course, these benchmarks have been optimized for both the migration architecture and the remote access architecture. So I think they're pretty comparable. But the real money shot here is the traffic. The amount of on-chip traffic that we can save is huge. For some benchmarks, we can save, maybe 2/3 of the traffic, and for some benchmark, we can reduce the traffic by up to 14x. So this is a pretty significant amount. So, in conclusion, what are the good things about it? Well, it significantly reduces the amount of on-chip traffic, so the dynamic power, if you have the right kind of workload. It's pretty simple to implement. I mean, this whole design from RTL to tape-out took us, I don't know, 18 man-months maybe. And it's very easy to scale. So for example, if we had twice the area and wanted to make a chip that is twice as big, we would only have to add 1 bit to the sort of core ID field in our processor. Some of the challenges that we are working on still are, well, workloads need to be optimized. You have to keep in mind that the memory is sort of split across the different tiles. This is kind of like optimizing your code for a cache coherence protocol, where you don't want it to sort of, you don't want 2 cores to have full sharing of the same cache line, but it's sort of more coarse-grained. But doing this automatically for a large program, it's not a trivial thing, and that's something we're still working on. On the other hand, I think there are significant opportunities here. So we view migration as an enabling technology. I have only shown you here how it can be used to accelerate memory access and to reduce the on-chip network traffic. But you can also imagine that, because this thing is very, very cheap to do and it's very fast, you can imagine having some small cores that are running some threads and some sort of fatter cores that, I don't know, have an FPU or are out of order or superscalar or who knows. And you can very quickly migrate the threads in response to program patterns. So we're sort of looking at this as an enabling technology, and we're looking into how to leverage this in other ways. So thank you very much. I will take any questions.
Okay, questions? Would you identify yourself and your institution?
Mohammed Abdullah, SMI. A question for you. When you did the comparison in the performance,
yes,
did you do that against the stack-based architecture? And did you try to do the comparisons with a traditional, registers type of architecture? And the second question is, can you actually implement your architecture with the same efficiency that you showed if you didn't have the stack architecture? Because obviously you're trying to minimize the number of state that you migrate in terms of the registers that are needed to the least recently used.
Yeah, so
last recently used.
Yeah, so thank you for your question. So for the first question, yes, the comparison that I showed was both designs were stack-based. It was basically the same architecture, except one of them had the migration enabled and the other one didn't. So in fact, we ran all of our experiments that these results are coming from on the RTL of the chip that we taped out. And for this reason, we couldn't run the same exact experiments on the RTL given a register machine, because we didn't have one implemented. However, we have done experiments with this sort of at higher level simulation with register-based machines, and this, you still get improvements. So, depending on what the simulator is, so it's not quite as accurate as RTL, right? So these results that I have shown you are from RTL, so they're rock solid. The other question that you had was, well, can I do this with a register machine? The answer is yes, but it's a little more tricky. As you pointed out, in the stack, the stack sort of naturally gives me the most recently used area, which will be on top of the stack. And so I can sort of just have one dial to turn to decide how much of the context to migrate. You can certainly do this in a register-based architecture. You can have this table that you keep track of what has been recently used. We do this for caches, right? If you have a multi-way cache, and we sort of keep track of which one has been most recently used, and this works pretty well. So
over here, name and institution.
Yes, it's Robert Micklin from Ascenia, and my question for you is just how much how much non-automatic work did you have to do on those benchmarks to get them, for them to become migration friendly?
Yeah, so this is a very good question. So we started out I think most of these benchmarks, we started out with a compiler that we had written that generates stack-based code. But this compiler, it's not, it generates good code, but it's not fantastic code, and it takes a long time to build a good optimizing compiler. So we had to tweak it quite a bit, but we had to tweak it quite a bit for both the baseline architecture and for the migration architecture. So most of the things we had to tweak actually had to do with the stack architecture rather than the migration versus not. But certainly we made some optimizations, keeping in mind that we could bunch up these accesses in one place and sort of then migrate and bunch up, make another bunch of accesses to another local slice. I think this is something that a compiler should actually in principle be able to do. It's just that today's compilers don't do it because they don't have to, right? So.
Yeah, so just a follow-up. So what you're saying is that you didn't do any hand optimizations to this code that you don't feel you could write a compiler to do automatically, right? No. Eventually, given the developer time to do that.
Yeah, I would say that, as with any architecture, right, you can always hand optimize something, right? Right. But we run the same code on both the RA and the EM versions. And I think it ran as well as it could on both, basically. And I think most of the optimizations, if not all of them, certainly the sort of pipeline optimizations as to if you know where the data is, then you can certainly decide to sort of bunch up your data accesses in one place, right? Compilers generally tend to reorder loads and stores anyway, right? So they can do this. The real trick here is that how you decide where the data should be allocated, and that's something we're still working on, right? Because you have to split the data over the whole chip. So you have more, on the one hand, you have no duplication, so you have more cache area total, but on the other hand, you have to sort of be smart about right? So,
over here.
Okay. Hi, this is Sarah Biabani from Intel. So you gave us some good latency numbers for the migration times, and you kept them per tile, where the locations were. But could you tell us a little bit more about the per tile predictor, the overhead of the prediction itself, and how that varies with different workloads?
I'm not sure what you mean by overhead of prediction. So versus a hand-optimized version?
Yeah, both. I mean, how are you gauging the time you take to determine how to move?
Well, so the predictor is actually pretty responsive, and if you're running the same code path several times, it will very quickly learn that it should migrate, right? Because the first time around, it detects that you've made 17 accesses to core 7. Then next time around, it will migrate, right? And if you're in a loop that executes 100 times, then you have effectively mispredicted once, and you have predicted correctly the next 99 times.
So
sort of like
are there any delays associated with loading up those tables that control whether things move or not? I think that might be part of the question.
Yeah, for instance, yeah.
So there are no delays. So in our design, this table is basically a bunch of registers. And it's actually pretty small. It's, I think, 32 registers or something like that.
So you don't have to stop work to change those tables?
No. So this happens entirely in sort of on the side. And the lookup itself, we can start the lookup as part of the pipeline because it is based on the instruction address, right? So while we're fetching the instruction, we can in parallel look up whether we think this instruction should migrate or not. So by the time we have the instruction, we already know that, whether or not.
Well, I'm thinking, like, the analogy with branch predicts and mispredicts, so you could kind of keep statistics like that, which would depend, of course, how well you predict based on your workloads.
Correct.
Over here, John.
Hi, John Mont from NVIDIA. I was trying to understand a little more about how the predictors work. It looked, I inferred that you had one predictor per tile. Do the contents of the predictor table migrate around with the work that is migrating, or do they stay in one place?
That's a very good question. That's actually two questions combined in two, right? So one, there is one predictor per tile. So the predictor is entirely local, right? So this makes it very scalable. And the contents of the predictor do not migrate with the thread. And so the reason for this is, one, it reduces the migration size. But the other reason is, if you think about a sort of a piece of the program that works on some data set, and it works on some data sets that's stored in one tile, that tile will already have the predictions for that piece from the last time around, right? So you sort of, again, it's a situation where you might effectively mispredict. Once you might hit an empty predictor, but on the other, when you come back, then the predictor has been filled. And the same is actually true for things like the instruction cache, right? You might migrate, you might have to fetch the next instruction, you might have a cache miss, but the next time you do it, it will probably already be in the cache.
Okay, so if the table didn't move and the work moved, does that mean there are little messages traveling back from wherever the work moved to update the predictor that was left in place?
Yes and no. So when you migrate back to that same core where you sort of started, where you're born at, if you will, you're sort of, we call it the home core or the native core, then you carry with you some information about how many accesses did you do to the local whatever next level cache on the remote core. That is to say, was it worth it? And the reason why you migrated back. So maybe you didn't have enough data, you had too much data, somebody kicked you out, right? And so this information is used by the predictor to learn once you have come back. So.
Okay, over here.
Hi, Charlie Demergent, Semi-Accurate. When I first saw your architecture, I thought, well, that looks like the next logical step to Tilera, which had similar origins to you. I think it was an MIT project, if I remember correctly.
Yeah, it was based on raw.
Is there any learning from that? Is it an evolution of that, or is it just completely separate that ended up in the same place?
So this is completely separate. We, of course, know about the work that was done on raw, but there is no overlap either with Tilera or with raw. The goals of our projects are entirely different. We're basically optimizing for migration, and for raw was a very different goal. One interesting about Tilera is that they started out without cache coherence, and they went and put it back, right? So one interesting question is, well, can we sort of combine cache coherence with this, right, and get even better performance, for example, right? Because they decided it was necessary.
Okay, one more question over here.
Roger Doring, Cal State East Bay. It seems like the problem of orthogonality of address spaces between instructions and data would cause you to be popping back and forth excessively. Can you talk about that?
I'm not sure what you mean by orthogonality.
Well, in other words, the address space that you're executing in has nothing to do with the address space of your data, and so the level 2 caches would be different for those two spaces and be causing you to hop around a lot.
That's correct. So in our design, our instruction cache, which I actually didn't have time to talk about, our instruction cache is basically read-only. That is to say, if you want to flush something out of the instruction cache, you have to do it via software, right? So it can cache anything. So any cache on the die can cache any instruction at once. So there's no.
But then when you hop, you don't have those instructions at your destination. So if you're in a loop and you've just moved to the next section of the array, you might have to bring over 20 instructions from the level 2 for.
Yeah. So what happens is you sort of mispredict. So you move over, right, to a new core. Maybe you have not run there before, and that core doesn't know about any of your instructions. And so the first time around, you're going to have a cache miss. and you're going to spend some time fetching the instruction and so forth. But this is, again, one of those cases where you mispredict once, but then if you're on that core long enough, you have, I don't know, 10, 100 loop iterations on that core, then it's worth it, right? And in situations where you've also been there before, probably recently, then that instruction will also be there. So.
Okay, we're running over a little bit, so Mieszko will be up here after the session to answer any additional questions, but let's thank him for an interesting presentation. The next paper is Intel 4th generation core processor, Haswell. The presenter is Per Hammarlund. Per is a computer architect working at Intel. He did his PhD in computer science at the Royal Institute of Technology in Stockholm, Sweden. He joined Intel in 1997 and has since worked on products such as Willamette, Nehalem, and now Haswell. Per?
Thank you. So, last presentation must have been good because most people are not sleeping, so that's a good thing. So, I'm going to try to cover a lot of ground today. And contrary to the previous presentation, you can actually buy Haswell in the store right now. And yes, I'm not going to tell you everything. But I'm going to try to give you a feeling for what we've done. So Haswell, to begin with, is not just one chip or one product. It's a family of products. So in the lower right corner, you can see some of the different die that we enable. So up front, we actually architect for an entire family. So we can then very efficiently sort of cram out die that fits to desktop, to mobile, and so on. And I'll talk about a few of the different configurations we do. The other thing is that we've introduced a new low-power platform that I think you've seen some of the reviews on the MacBook Air, giving really good battery life. So that's this low-power platform that Apple is making really good use of. Some of the idle power characteristics are 20 times better than the previous generation. We have a really, we think, exciting variation of it that has a huge eDRAM cache that's great for graphics performance. I'll go through how that works. We've done a lot of platform enhancements, for example, panel self-refresh, which is another great thing for low power. We've introduced fully integrated voltage regulators, and I'll go through what benefits that has on a couple of walls. Sort of buried in all of this, we also have a great core. And this core, we developed this in the context of the client part, but this core gets reused as is for the server part. So it has a lot of features that are both good for client applications, but also a lot of features that are great for server applications. So FMA, 2x the cache bandwidth, new synchronization primitives, and so on. Then also buried in there, we have really good graphics, and I'll show some performance numbers, both on our graphics performance, the new standards we've added, and then the media characteristics, where we have some really nice both enhancements in quality and enhancements in power and performance. So when you build a processor like this, it really, really helps that your company can afford a $10 billion fab. So just to give sort of the context here is that Haswell is in this succession of Tock, where we build, in the middle of a process technology, we build a Tock, a huge microarchitectural change. That's what Haswell is, a Tock, a big change. Then when we go to the new process, we actually do much fewer changes in the microarchitecture, but we take full advantage of the new process. That's the TIC. So Haswell is in the middle of the process, the 22 nanometer process. It follows on the microarchitecture on Ivy Bridge. That was the TIC that started 22 nanometer. Some of the really good things for us here were the 22 nanometer Tri-Gate transistor, which is much faster, lower leakage. And we also did a few enhancements like adding metal layers for greater density and actually lower cost at the product level. So let's just go first to sort of power efficiency, which is sort of one of the main characteristics you need to improve. Because pretty much all, including servers, all of our uses are power limited, right? We're trying to lower the TDP, go into smaller form factors year over year. So what we need to do to keep the performance the same or go up is actually to improve the power efficiency. So when you look on the things we do on the sort of power performance curve, when you do voltage frequency scaling, we're trying to push that curve down so you get the same performance at lower power. So we increase the turbo up in the right-hand corner of that graph. We actually increase the turbo range so you can get more burst performance. We improve and add new C-states for more efficient power. We improve the latency because the quicker you can go in and out of C-states, the more aggressively you can go to lower C-states that save power. We continue doing a lot of focus on power gating and clock gating, so everything that isn't used is always turned off very aggressively. And then the last thing we do, and I spoke about it a little bit with the process, is that we collaborate with the guys who define the process and the transistor. They're just a couple of miles down the road, and we make sure that we build transistors and design the part for the process. On top of all these sort of general statements, what we've done is gone in and try to make things more independent. So we actually set the frequency and voltage more independently on Haswell than previous generation. That allows us to, between caches, graphics, and cores, we can shift the power to the place where the power is used the best. To actually, for a fixed power envelope, we put the power into the unit that gives you the best performance experience for that. So if you're doing a graphics-heavy workload, that's where the power will go. And all of this is done dynamically by the power management unit. Then another thing we've done is we've added new power management states. So the old way of doing things was you had active state and sleep state, and you could jump back and forward between it. On Haswell, we've improved the old way of doing things. So we've lowered the power for the active state, and we've reduced the latency of going in and out of the sleep state. That's all good. But what's really cool is that we've, let me build this out. We've added this new sleep state where the CPU appeared to be active, but in reality, the platform has the power characteristic of being off. So this is what we call the S0IX state. It's an active idle state. And this is where we can see for the low power platform a 20x improvement in the idle power. So the OS, this is completely transparent to well-written software. Meaning OSs that don't do funny things will get this benefit of the hardware automatically, instead of going to a sleep state, it will just turn itself down to very low power in what looks like an active state. And the key technology there is really that you can come in and out of this state very, very quickly, so that you don't break the OS that is sort of counting on the hardware being active and responsive. Here you need to go into a very low sleep state and come out of it, making the OS believe that it was always active. And this comes also not just the CPU, it also goes with the platform, that you need to completely power manage the platform and turn on and off all the devices in the platform too. So Haswell, essentially when you're running on your MacBook Air or something, is always in this mode. It's almost sort of utilization-wise always turned off. So, next cool thing, fully integrated voltage regulators. So, if you look at the Ivy Bridge platform, we had a whole slew of highly optimized voltage regulators, and that was all good. They provided voltage at the right characteristics for the different pieces inside of Ivy Bridge. In Haswell, what we did is we aggregated all of those into a single external, well, except for memory. Memory stayed separate. But the four above, we aggregated those into a single external voltage regulator. And then what we do is we supply one voltage into the chip, and we do the voltage regulation on the package in the die. That allows us to actually break up at the same cost. We can break up and give each unit a much more fine-grained control of what voltage and so on it wants. And it has a lot of other efficiency improvements too for us. But one of the really cool things is that when we look at the same chassis mobile application, the top one is an Ivy Bridge board, and the bottom one is a Haswell board, you can see how much reduction of board space we achieve. On this particular application, and it's different between different uses, you get about a 3.5x reduction in the board space. So in this case, since it's the same form factor, they didn't build something smaller, but all of the things that are Haswell or core related shrink by quite a lot. So the board space goes down, the number of passive components and so on the board goes down a lot because we've moved those inside the package and the CPU. You free up, in this particular application, they took a little bit of that saving and turned it into extra space for the battery inside the chassis. So they could build with a 10% larger battery. So the form factor here shrunk, in this particular case, by 2 millimeters. Since there are fewer parts on the board, we saved about $5 in this case, and 10% more space for the battery. And I think in the next generation, when people want to go through and build a new chassis, they can actually cash in on this PCB board area saving and build an even smaller motherboard and potentially go after new form factors. So that was FIVR, giving us both efficiency improvements and also giving us a lot of platform goodness. Okay, so now cache hierarchy and interconnects. Since we're improving the performance quite a lot, and I'll get to the instructions we added in a bit, especially around FMA, it was really important to improve the cache bandwidth and efficiency. So some of the things we did was we went through, we have this on what's called the LLC here, the last level cache controller. We went through and essentially re-microarchitected that so that we had separate pipelines for different kinds of requests, and that allowed us to substantially enhance the utilization of the cache array itself, so we overall got better bandwidth out of it. We improved, there's a lot of heuristics when you have both the cores and graphics and media and display sharing the memory and the cache performance. We improved the heuristics and the algorithms for sharing the bandwidth substantially, so that again, we got better utilization out of the system. We went through and re-architected and re-micro-architected our memory controller so that we had much better DRAM write throughput by having deeper pending queues, more decoupling of different kinds of requests, and better scheduling. And then the standard thing is that we always look at an algorithm that implements something, a microarchitecture algorithm. We will go and look at it to see, can we do that same thing with less power? Meaning we take a perfectly good microarchitectural algorithm, come up with something that's better, and re-implement it and save power. So that's really a lot of what we do, is to go through the microarchitecture and just continuously improve it. So that was enhancements on the cache and interconnect. So then we come to what's a pretty exciting part, and this is the crystal well part that is coming out. We added one of the die we have has a huge cache. It's 128 megabyte eDRAM cache that can be shared between graphics and cores. So you can do really good data sharing between all the compute elements on the die. We architected it for very high throughput and maintaining low latency. I'll show some numbers on that. So what we really wanted to do was to make sure that it was easy for people to code to it. Because there was a lot of skepticism, I think healthy skepticism, whether caches would work for graphics workloads. So we did a lot of work to make sure that we understood how graphics workloads actually behaved. And then we architected this cache solution to make it work. And as I said, this is fully shared between the graphics, the media, and the cores. So that you can do really efficient, if you write for cache, well, you get actually really good behavior even with your random code, we've found. But if you actually do some amount of coding and optimization for utilizing the cache, you can have extremely good, efficient computing through this huge cache. So just sort of a couple of hints. Why does this work? So with Sandy Bridge and Ivy Bridge, that has fairly big caches, 8 megabytes and so on, we showed that it was easy to get, or you could get good performance, 20–30% improvements inside of a frame because graphics does a lot of things like reusing content, like smoke can be the same pattern just written multiple times, and so on. So that we already proved in the Sandy Bridge, Ivy Bridge generation. What we went after with the bigger cache in Haswell is that you can even get between multiple rendering passes, you can get reuse of data. So when you look at a cache that is in the 16 to 64 megabyte range and above, you can get another 20 to 30% speed up by reusing the collateral that is in the first frame, the second frame, and the next frame. So just looking at this educational application, you can see that something like the airplane gets reused, a lot of the textures for smoke and so on gets reused. And all of those things remain in the cache between different rendering passes. So for us, building on the benefits we got out of Sandy Bridge and Ivy Bridge with its caches, providing an even bigger cache together with an even bigger graphics engine, Kristopher gives really, really substantial integrated graphics performance characteristics or performance numbers. Here are a couple of examples. I won't walk through this. You can look at it on your own time. But I wanted to just show you the sort of over-architecting or over-design we did on latency versus bandwidth. Typically, when you utilize DRAM, you will have this behavior that your latency goes up. We made sure that this first generation of a cache like this would have an easy-to-use, very flat latency curve, sort of insensitive to utilization, so that inside of the typical behavior or the typical use of bandwidth, you would have a good latency characteristic. OK, graphics media. We did a number of optimizations because we're providing essentially 3 levels of graphics size, right? You saw those die photos or the pictures on the first slide. We've built the graphics block and the media block such that you can scale it. So there it's broken down into 6 scalable domains. One is where the global assets are, the front end, the setup engine, if you will. Second is the common slice, where the rasterizer, the cache, and the pixel backend live. Then you have 2 sub-slices, where the execution units, the instruction caches, and the samplers live. And then you have a number of video codecs, multi-format video codecs, the video quality, and I'll talk a little bit more about that, video quality enhancement engine, and the display engine. So since we've broken down graphics into these components, we can then scale, for example, the number of EUs and the number of slice commons and sub-slices to give us a fairly wide range of graphics performance without having to redesign the entire solution. We have added a number of improvements to our video codecs, setting up for a hardware-based scalable video codec. We've done improvements to the MJPEG hardware decoder. We've done all kinds of improvements to allow the 4K video playback power efficiently, and I'll show some numbers on that. And there's just a whole slew of sort of incremental enhancements we've done to the video and media system. And again, here's a list that you can read in your time on all the various new algorithms and improvements we've done to make the quality of video on a Haswell be much better and give you a better experience when you do video playback. Here's a couple of numbers. Again, this is specific, our configuration dependent, right? So some of the chips we do have 4 to 12x real-time transcode at various quality modes. We enable, with the new power efficiency of the media block, we enable the 10-hour video playback on the latest MacBook Airs. We can do multi-stream 4K decode, and we can do greater than real-time 4K encode. So on one particular example here, we speed up by 5x at the same time as we consume half the power. So that was graphics and media. Let's go through the core. We've done a whole slew of what we typically do, sort of IPC, instruction per cycle improvements, microarchitecture tweaks, better branch predictor, very much improved front end that works especially well for sort of large code base applications like databases and TPCC and all the follow-ons. We've done the deeper buffers, and we've done a lot of simulations, and we've adjusted the algorithm such that we're still power efficient with those deeper buffers. We don't sort of over-speculate to do anything strange. We've added execution units. We've added a lot of load and store bandwidth, and I'll show a couple of foils on that. And we've done all of this without changing the pipeline stages by much. The reason for keeping the pipeline stages the same is that code that is highly tuned for the microarchitecture, we don't want that to have to be retuned between generations. We just want it to run and run faster. So first one is buffer sizes. Within reason, we've notched everything up just a little to make the machine more efficiently speculate more deeply. Let me build this out. If you look at the compute elements, we've added twice the FMA capability, and I'll go through that a little bit more in detail. We've added a fourth ALU, again, to match up with the workloads we do when we run twice the floating point content. We need to also have a matched set of ALUs to get all the integer work at the same time done. We've added a new branch prediction unit. We found that a lot of code has a surprising amount of branches that go through at the same time that you need to sort of plow out of the way so that they don't reduce your utilization of other functional units. And we've added a new AGU for the store port. So again, when you're running a highly tuned floating point workload, you can get all your address calculations out of the way to make sure that you're really utilizing your floating point units. OK, so here, I think this was a really cool microarchitecture and implementation that we did. We added 2 new FMA units, so we doubled the floating point performance. We also doubled the bandwidth in the 2 first-level caches to actually keep up with this doubled compute performance. The other thing that we did that I thought was really nice was that the latency for doing an FMA operation, floating point multiply add, went from 8 cycles, if you did it with 2 instructions in the previous generations, to 5. So our FMA latency is the same as the latency of the multiply in the previous generation. So not only did your compute performance for workloads that can use FMA go up by 2x, we also made the latency when you're doing aggregations, scaling aggregations, and so on, that latency went down by 1.6x. These are just some numbers on the parts of the cache hierarchy where we went in and doubled the bandwidth for load and store performance. And we also substantially increased the size of the second-level unified TLB. Again, this was an improvement primarily for server applications that have a huge code footprint to make sure that they can have easy access and efficient access to translations. So ISA, just going through this real quickly. We did the vector enhancements, like I talked about. We also fleshed out over Sandy Bridge and Ivy Bridge, have the full complement of 256-bit vector or integer vector instructions. We did gather instruction, and we did the full width element permutes. And jumping to this, we added a fair amount, and we sped up a fair amount of instructions to improve our cryptography performance for various kernels. And this is really highly used in Wall Street applications, in data centers, and so on. So this is an important area for us to speed up the CPU. And we have some really nice speed ups with the new instructions we added. Locks. not only did we speed up locks, just lower latency for cacheable locks, we also added hardware lock deletion. So if you put a hint on your acquire release, you can do lock deletion so that you can actually run 2 locks at the same time. They appear to both acquire the lock, but as long as you don't conflict on the data that you use or produce, they run in parallel. We added restricted transactional memory with new instructions, so think of this as a lockless critical section. So typically people think that transactional memory is only for databases. So let's show some high-performance computing workloads, where on this 4-core HT system, you can get some really nice speed-ups, because in complicated HPC codes, when they update the compute elements, right now they need to have locks. And we can do this with transactional memory, and we can get much higher performance by avoiding these cases where you conflict on data. Virtualization, we've continued removing latency in switching in and out of the host. We're much more efficient. We're now below 500 cycle for a round trip. And we've added some enhancements architecturally as well. So this was the flyby of all the different features we put into the Haswell core and client products. And I think we have a few minutes for questions.
I'll bet we have some questions. Why don't we start over here? Name and affiliation.
Devjit Dasharma from AMD. Couple of questions. One is, I think for the integer execution unit, you showed unified reservation station with 8 ports. When you say unified reservation station, I'm trying to understand, does it mean, for example, you have 2 FMA pipes, right? That you can have 60 FMA ops to pick from in any cycle from this reservation station?
So, yes.
Okay, so it's truly unified. Okay. The other question is, in the previous generation parts, you had 2 floating point add pipes and 1 floating point multiply pipe. I understand that you have gone to FMA, and I think you get 2 multipliers free because of that. But you have now only 1 floating point add. For code which doesn't have FMA, floating point adds outnumber the floating point multiplies. So do you see that as a problem, that for code which is not Macified, that you have less add pipes than mul pipes in the floating point unit?
No, so we're still a superset of the previous generation. We can go through that together. So code will run the same as the previous generation.
So that means you have 2 floating point add pipes?
Yeah.
Okay, thank you.
Over here, name, affiliation.
Michael Deering, Photon Wall. Some real great work in the inside of the instruction execution and other levels, but my question is, in terms of things that are new, as you mentioned a couple of times, support for 4K video. Now, I know there's some real problems with the current interface standards. Right now, I run 2K video at 120 hertz for stereo. My understanding is the only 4K out there right now is 30 hertz, and it's really only meant for movies. So I just wanted to specify what sort of frame rate did you mean by 4K?
So I would have to get back to you on that, but I believe it's 30.
Thank you.
Over here.
It's Ando, Micron. I have a question regarding your fully integrated VR. And may I ask exactly what's on the CPU chip? Or is it separate VR chip?
So there was a really good article by Mr. Cantor a while back. He's over there. It's probably the most information you can find that is not confidential. So one way to view it is that everything that is not the inductors are on the die.
CPU die?
Yes.
And you have mentioned that higher efficiency. Can you disclose the efficiency and buck converter frequency?
I think the best way to do that is you can buy the chip and you can measure it.
Okay.
Thank you.
Over here.
Don Draper from Oracle. That I/O port you had between the CPU and the eDRAM, how wide is it? What's the latency? What's the bandwidth?
So you saw the latency is around 50 nanoseconds use, even loaded. You can think of it as 50 gigabytes per second bidirectional. And the width it's on the die, so you don't sort of see it.
Okay. That the eDRAM is part of the same piece of silicon as the CPU?
No, it's a separate chip. It's a proprietary cache that we build on our logic process. And we put them together on the same package. So it's a multi-chip package.
Yes, thank you.
Over here.
Yeah, another eDRAM question.
A name?
Jeff Stukley at IBM. So I guess two questions. One, I assume the directory is, or where is the cache directory at?
The directory is on the die.
On the processor die.
Yeah.
Okay. And how do you make allocation decisions? Does everything go through as a victim cache, or is there some way? It sounded like you talked like you could tune or specify things that got allocated or didn't allocate it.
I think that we have a number of different modes. We found that for most codes, unless they're highly optimized, just using it as a regular cache, not exclusive cache or anything, just as yet another cache level is the most efficient, well-rounded way of using it.
Okay. Which is when you evict from your last level cache, you write it into the next level. Okay. And then it goes back out to memory.
Yeah, when you need it. When you need that location.
Over here.
Thanks.
Sam Nafziger, AMD. So adding 2 layers of metal, that's quite a step for Intel. Not quite to IBM levels yet, but a lot. Could you comment on the motivation for that? Did it have to do with IVR or just SoC composition improvements?
No, so even though it sounds strange, we added the metal layers to reduce cost. What we found is that for the kinds of parts we're putting together, we can increase the density more than we pay for the extra metal layers. So it actually comes out of both sort of a performance enhancements, because we can use it for a lot of cool things, but we also increase the density. We pay a little bit more for it, but it comes out as a net benefit for us. I'm not sure we'll get to IBM numbers anytime soon, actually. We'll see.
Over here, one more.
So Stephan from Oracle. So I have a question about the C state you mentioned in your slides. So you said you improve the C state latency, and I want to know like how much it got improved and how important it is in your power saving techniques.
So I think in the IDF presentations, there is actually a table that spells out all the new states and the latencies. So I can point you at that. Depending on which C state it is, you can view it as between 20 to 30% improvements. What that means for us is that we can be, since all of our C state transitions are essentially automatic, if you will, that means that you can go deeper and come back out in the same amount of time. So if you look at the power you consume, you're just saving more by being able to use deep C states more aggressively. So it plays a huge deal in making sort of an incremental enhancement across the board to power efficiency.
Thanks.
Okay, well, this has been a great pair. Let's thank him again for a fine talk. And our final talk for the session is Microprocessors for Roots of Trust. The presenter will be Chris Carver. Chris is technical director at Bluerisc. He's been with the company since inception. He was a key architect in Bluerisc's TrustGuard security-focused microprocessors and associated platforms. Chris specializes in secure processor architecture, reverse engineering techniques, protection architectures, as well as state-of-the-art attack models. Chris?
Thank you, Forrest. So today, I'm going to be giving a bit of a different perspective to the term computer architecture or processor architecture, and that being from a security standpoint. I know disclaimers are not what you enjoy, but I do have one, given the sensitive nature of some of the deployment scenarios where this is applicable. I may not be able to answer all of or any of your questions in complete depth, but I will do my best. Related to this, just want to stay up front that we aren't necessarily trying to build a secure processor to replace a Pentium or replace an x86 core. We're creating a secure processor for the strict opportunity to insert this security in the system and add a root of trust. This is obviously very applicable in the defense applications. As you know, they contain many security critical algorithms that if someone were to get their hands on would be very beneficial to someone else. These will often come in the form factors of embedded systems, and these are primarily FPGA based. So many of the systems that we work with have one main processor on them. They're sort of a hybrid processor as well as a configurable device. So the processors that I'll be discussing today are mainly targeting instantiation into the FPGAs. In addition to the defense systems, we also have, there also are many high security commercial systems that are not only already present, but are emerging. So before we get into roots of trust and the underlying architecture, wanted to take a minute to go through a traditional security mindset and how I believe it's flawed. In many cases, security is added as an afterthought, and this is traditionally done through the incorporation of a specifically designed software, a specifically designed hardware module that's added to the system to play some security role. Now, unfortunately, this software and hardware are based on conventional processors and conventional ISAs, and this being the case, they're susceptible to many different types of attack. One of this being the software reverse engineering attack and malicious modification. So in many cases, an attacker may want to just either know how your stuff works or be able to replicate that and sell it themselves. There are also some side channel attacks, such as fault injection, in which someone will try to play with the inputs to your system and bring the state of the system into an unwanted state in which it may leak some information. And then one of the more popular attacks, the side channel attack of power analysis. I'm sure you're aware, but cryptographic implementations are susceptible to a power analysis attack in which the power profile of the algorithm is correlated to the underlying algorithm, and the key can actually be extracted through those means. What this results in is the actual opposite of what a protection architect would want. Typically, you want to reduce the attack surface of the system that you're protecting. But what you find is actually, in many cases, you've actually increased it. And that's because not only is what you're trying to secure no more secure than it was before, but the security you've added has holes in it. This is one of the things that we're trying to address. So how are we going to address this? The goal of this is to break the attacker's assumptions. So we want to break the assumption that there is a static ISA encoding that translates to a single underlying operation. This will aid greatly in defending against reverse engineering attacks. Secondly, we want to be able to control the power profile of the execution on a core and break this power profile to execution correlation that typically exists, aiding in protecting against a differential power analysis attack or a simple power analysis attack. Lastly, timing is something that we can control. So many fault injection attacks rely on being able to identify a specific time at which something may happen such that the attack can be mounted. If we can break this assumption, then I think we're doing something good in getting towards an inherently secure solution. Once we can sort of build these into our core, as I'll show we do, we can then use this as a root of trust for the system as a whole, and we can transfer that trust to other components that are running in the system with the ultimate goal of increasing the time and cost of an attack to the point where it's no longer feasible. So how do we do this? Well, we propose and have moved the roots of trust into the processor architecture itself. So we've actually developed a TrustGuard family of processors that have all of the roots of trust built into them that I'll be discussing today. So the first level of root of trust is what we call a core root of trust. This is built into the architecture in such a way that we need to have one single trusted node such that we can build upon that trusted node and extend that trust to other components in the system. We achieve this through randomized ISA support that I'll get into in the coming slides, ISA support for power and timing control, again, trying to break the attacker's assumptions. And finally, secure storage. So obviously, the data side of things is very important, and we have to ensure that all of the data that is leaving the chip or is leaving critical portions of the chip is secured. Once we can do this, we can also start integrating at the architectural level other roots of trust, shared roots of trust that can be utilized by other components in a system. This includes root of trust for co-execution. So one usage model is to have our secure processor family playing the security role. Now, there may be algorithms or software running on a main system that only have a small portion of them that are deemed security critical. So being able to co-execute that security critical portion with our code is of interest in many cases. Additionally, key management. I mean, key management is huge. The impression I've gotten from speaking with a lot of people, nobody really knows how to do it. And having a key management functionality that is inherently secured is definitely a step in the right direction. And then finally, measurement, root of trust for measurement. Many solutions today rely on the ability to measure a system state and know if that system state has changed. And if it has, that may be the indication that the system is under attack. But one of the problems with some of the conventional means is that the measurements themselves can be attacked. By moving these measurements and protecting them with our core root of trust, that's no longer the case. So we'll start with ISA definition and encoding. This is one of the main components in establishing this core root of trust. So when we started this, we wanted to represent an ISA as a tree structure. As you can see here, we are able to. It actually lends itself very well to a tree. You have this tree itself is actually a 16-bit ISA for the purpose of example. It supports roughly 64 instructions. And each of the operations themselves are located on the end nodes. The leaf nodes. And the intermediate node and the root node contain information as to bit positions and opcode values and where the opcodes exist. So basically, you could take this tree and reconstruct the ISA in its entirety and map it to 16 bits. Now, since we do have it in a tree structure, we can actually change this tree structure. So we have one ISA, and if you can see, if I go back, this tree structure is different, but the underlying operations themselves have not changed. Just the encoding, so the ISA encoding has changed. And that's one of the key concepts that we will take further and build upon in the future versions that I'll discuss. But being able to create a previously unknown ISA encoding is a big step in breaking the attacker's assumptions. So one interesting thing to take a look at is how would attackers are not used to coming across a device they don't know. There's an ISA, and they'll find that, and they'll disassemble the code and figure out how it works from a reverse engineering context. How would we wanted to look into how they would actually attack a code that had a random ISA that wasn't defined anywhere, that they weren't aware of. In terms of simple complexity associated with the information bits required to encode all of this information, we came up with a value of about 340-bit. It would be approximately a 340-bit key. But one of the more interesting thought processes is the actual trials that would have to be performed in order to break this system. So an attacker would actually have to first define a test ISA. They would have to know the underlying operations and create an ISA and define that. And then they'd have to create a simulator to run this ISA, to decode these instructions. Then they'd run the code that they're trying to break or trying to reverse engineer. And then finally, they'd have to determine if the results made sense. And that's a non-trivial problem. So, I mean, you can have many ISAs that have been defined that will do something for you. Not all of them are going to simply crash. So that leads to even more thinking and more time and more resources that are required in order to mount an attack on these systems. But one of the benefits of this solution is that they have to do this for every possible ISA. So as you can see, rather than having a known ISA, the amount of work it would take to break an unknown ISA increases pretty drastically. This leads us to the first processor in the TrustGuard family of secure processors. We call this Tiny TrustGuard. It's a 16-bit core. Again, remember, we are targeting FPGAs. it operates on a per compilation basis. So essentially the way that this core works is it's generated by a toolkit. So we have a software toolkit that first defines an ISA. And once it's done defining that ISA, we actually create a compilation environment that is that is specifically created for that ISA. So a designer would have its GCC suite, but it's tied to this ISA. And then, which is an even further departure, is we actually generate the hardware. We generate a synthesizable code that will decode the newly generated ISA. So what this results is a developer can now have a toolkit that will create a completely compilation unique software and execution environment that can work in the scope of an FPGA. So compilation unique ISA is great, but can we do more? We've found that the compilation unique ISA is actually very relevant in many systems, especially super constrained systems, but we wanted to take it further. We wanted to make it device unique. And this brings us to the TrustGuard processor. TrustGuard enables a device-unique randomized ISA encoding and decoding as well as execution environment. We do this by an installation time component that actually ties what we call as sort of a meta format of an application directly to the device upon which it's been installed. And we do this through utilizing physical properties of that device. In addition to making it device unique, TrustGuard also has other architectural features that adds the ability to have fluidity in the ISA. So what I mean by fluidity is that depending on the path in which the program is executing, the ISA itself and the ISA encoding will change. And there's architectural support that enables that. So rather than an attacker having to try and figure out one ISA, based on how the software is actually executing, the reverse engineering becomes much, much more difficult because they have to be able to identify multiple ISAs depending on the execution paths. TrustGuard does extend Tiny TrustGuard. It's a 32-bit dual issue core. In addition to the sort of roots of trust for execution and randomized ISA encoding, we do have hardware cryptographic acceleration that's tightly tied into our pipeline. We have a DPA resilient AES module, SHA-1, SHA-256, and the like. We do have a hardware accelerated RSA that's implemented utilizing parametric Montgomery multiplication as well as some other components that are critical to the use of the processor. I'll briefly go through this. It just basically compares TrustGuard versus a conventional processor. On the left-hand side, you'll see the conventional compilation means source, binary, source compiler, and then you have a fixed ISA application. On the right, you see the TrustGuard process. You have a security-focused compiler that actually generates an intermediate format that once it's tied uniquely to that device, it results in a device-unique ISA encoding as well as a fluid encoding. I'll go into the details of the actual deployment flow in a bit. But this block diagram shows sort of the roots of trust that we've incorporated into the design. We have at the top one of the main roots of trust that I've been speaking to, or this enables one of the main roots of trust, is this runtime ISA definition. This is the actual hardware or the architectural support that enables the tying of a software uniquely to the device upon which it will be executing. And this obviously utilizes physical properties. In this example, we say that we have a puff. Puff doesn't necessarily have to be the case, but it is one option. This is tied directly into the root of trust for execution that we show here. This root of trust for execution not only pertains to the ability to decode these random ISAs and device-unique ISAs, but also the ability to control the power profile, the ability to randomize some of the timing of the events, and these tie back to some of the goals that I had brought up earlier in the talk. The last core root of trust that we'll introduce is the root of trust for storage. Obviously, you have to have a means for secure storage within a processor architecture, especially a security processor. This ties into our non-deterministic random number generator, cryptographic support, as well as some other support that we don't have shown here. But essentially, this allows us to encapsulate our device by cryptographic means. So in addition to the actual random ISA encoding and the random execution architecture, we can encapsulate the device from a cryptographic standpoint. Getting on to some of the more interesting roots of trust, remember that we have to establish these core roots of trust such that we can extend them to the system as a whole and actually protect some things that reside or may execute outside of the TrustGuard processor. One of the first things that we do have here is the root of trust for key management. This also ties into the non-deterministic random number generator, the cryptographic cores, and as well as the root of trust for storage. So being able to generate, manage, migrate, and kill keys for a specific application and do so in a secure manner is something that doesn't exist out there today. So utilizing our core roots of trust to enable this functionality is a very big benefit. Additionally, we have the co-execution roots of trust. This is the case that I had described earlier when security critical portions of the code may execute on TrustGuard while others execute elsewhere. Integrity verification, being able to attest to the state or the integrity of a protected application and do so in a way that can't be bypassed is obviously of interest. We have the root of trust for measurement. This goes back to the ability to monitor, read, store, and perform operations on specific system state and do so in a secure manner that can't be bypassed. So as you can see, all of these are sort of relying on this tamper-resilient execution environment that we've created to provide some of the more common security services that are required. Finally, one that's often overlooked is a response mechanism. So in many systems, the response mechanism is incredibly important. So what happens if you detect tampering? Well, if it's not done properly, the first thing that's going to happen is the attacker is going to remove your response mechanism. That's instinct. They don't want to get caught, and they're going to have to run multiple iterations likely to gain any real information. So your response mechanism isn't going to exist anymore. But if you're able to utilize our roots of trust and have this implemented within a secure execution environment, that's no longer the case. So since we are dealing with a different flow or a different sort of processor architecture than the norm, I thought it'd be interesting to show some of the tooling and infrastructure support, especially because when you're dealing with this from the security perspective, a lot of the things that are taken for granted in conventional flows are, you can't take them for granted in this case. On the left-hand side here, you see we start with a source level compiler. We have the option to insert some of our active security libraries and APIs into the code. This goes through our Bluerisc GCC with a Bluerisc backend, resulting in a binary. This binary then goes into our binary level optimizing compiler. We've actually developed this in-house. This compiler takes in a binary, performs analysis, performs translations, transformations, looks at the code, inserts things that we may need or meta information that we may need at runtime to enable the fluidity or to enable the device unique encoding. From there, it's fairly standard. You have functional simulation, cycle accurate simulation, and then you get into the deployment phase where things kind of change. As mentioned, we have the runtime ISA definition, which is definitely a departure from a conventional deployment. But around that, one of the major issues is debug. Debug and security are not friends at all. So we had to find a way to allow debug, because if we went to a customer and said, no, sorry, you can't debug your code, then they're going to kick us out. So we did. And we actually utilize techniques that are built into the roots of trust in our core to enable debug for a specific period of time and then disable it. And we disable it through a means that's similar to a hardware fuse, but it actually relies on software and ISA encodings. In addition to this, we have to also provision for installation in both trusted and untrusted environments. If we're working with the Department of Defense and this has to get deployed into some foreign environment or some DMZ, then we have to be able to install an environment where you can't trust the guy that's plugging this in. So architectural support for trusted and untrusted installation, and the entire protocol for doing that has also been developed. Finally, once debug is unallowed, you basically have your system. It's device unique, and it's running on its own. Hopefully that was the end of it, but it's not. As you know, once you've fielded a system, and many times you have to upgrade it because there are bugs, and there needs to be new functionality. So that posed another problem as to how we would support that. So again, we were able to utilize, one, the fact that we're designing this ourselves. We're working with a custom processor here, and one that's designed specifically for security, so that we could insert architectural components that would enable a secure field upgrade. So we have an end-to-end methodology as to how you can upgrade a binary or an application that has been uniquely tied to the device upon which it's executing in a secure way. So an end-to-end secure communication, and then the actual re-ISA definition of the patched code and things of that nature. So in closing, we were able to identify some of the key components that are typically overlooked and address them. Just to briefly touch on the performance implications before we get done here. Since we do have control of this, especially with Tiny Trust Guard, we're utilizing a parametric decoder, which this actually results in a fairly minimal cycle time overhead. With regards to Trust Guard, again, we've been able to minimize any performance impact of the fluidity of the ISA. With regards to the ISA redefinition, that actually only occurs once at start, so there's really no performance impact there. We've done tests, and it shows that roughly 1%, less than 1% performance impact over a design containing compiler-only techniques. And we have achieved 1.5 DMIPS per megahertz with this full new mode of execution. Briefly, the integration options. Obviously, one is embeddable IP within a FPGA system or a hybrid processor FPGA system. But outside of that, we actually do have form factors that are available that contain these cores or other TrustGuard processor family cores. The Express card, PCI Express, these are available off the shelf with complete design environments and all of the design deployment and maintenance support. We have gone down the ASIC flow path, and we do have an ASIC flow developed and available, but we have not taped it out. As we've gotten into deeper discussions with customers, we've realized that FPGAs are pretty good right now, and we have yet to tape out the ASIC. So that is what I have. I hope that, I know it's a departure from the power, performance, and in memory sizes that you're used to, but I hope it was interesting. Thank you.
Thank you. I have a question over here, name and affiliation.
Hi, Sima Setumadhavan, Columbia University, very intriguing work. So there's some concern now that hardware used in high-value, high-security systems can be backdoored at design time or at manufacturing time to compromise security at a fundamental level. Do you have any protections in your system to protect against such hardware backdoor attacks? Because you mentioned something about tampering and sensitive versus insensitive installation.
So can you speaking to hardware Trojans, that type of technology?
Yeah, things that can be a malicious designer on a team, or malicious third-party IP, a bad CAD tool, or untrusted foundries, any of those.
Well, yeah, I mean, it's possible with the untrusted foundries, but we're not dealing with foundries directly. We're utilizing FPGAs. But with regards to the other points, the underlying the sort of core root of trust in the ability to actually be able to properly decode these instructions and properly handle the keys. Even a very small alteration in the device, since we're utilizing the physical properties of the device in the creation of these instruction sets, would likely result in it would be caught immediately during test. So that's I think the level of answer I can give you at this time.
Okay. Another question?
Sure.
Okay. So let's say an adversary basically tries to inject code.
Okay.
Doesn't know your ISA.
Yeah.
So the program basically crashes and dies?
Well, the program will immediately go into an interrupt handler. It's not going to break the code. I mean, they've just injected code that can be handled. That actually is an ideal tamper response mechanism. So we have an immediate tamper response to malicious code injection because they don't know the ISA. If they inject code that isn't properly formatted or properly encoded, then it's going to go to our exception handlers. And from there, it's up to the system developer to decide what they want to do. It doesn't kill the system, though. The system will still run.
Okay, thank you.
Okay, John.
Hi, John Mott from NVIDIA. With all the care you're taking in all these different areas, it seemed a little ironic to me that open source GCC is part of your flow. Is that, is there anything you do specially about that? Do you somehow qualify new drops or anything like that?
At this time, I know this was obviously started quite some time ago. I'm not the GCC guy. I do know it is part of the flow, or at least in the beginning it was. I can definitely get back to you to address that question. I don't have the answer to that question right off the top of my head.
Okay, one more over here.
Sure.
Alan Baum, Retirement Inc. You said you had a non-deterministic random number generator.
Sure.
But you're putting it on an FPGA, and I'm wondering how you do that.
I'm not going to tell you how I do that.
Okay, thank you very much, Chris. That's great.
Thank you.